All right, in this lesson we're going to look at integrating equations that have both x and y in it. So it's working backward from implicit differentiation. So remember, with implicit differentiation we were finding the derivative with y and with x. So now we're going to find the antiderivative of equations that have y and x. So the method we're going to use is called separation of variables, because we need to have the variables isolated on opposite sides of the equal sign so that we can integrate them separately. So let's do this. Now, important thing to remember or to know is that when we do find an antiderivative, both dy and dx need to be out of the denominator. So in this case we have dy over dx, and dx should not be in the denominator when we find an antiderivative. Let me show you what I mean by that. So if I move the dx over to the other side, I end up with dy equals x over y dx. And what that tells me then is that all of my y's are going to have to be on the left-hand side with this dy, and all of the x's are going to be on the right-hand side with the dx. So that helps me understand when I do separate which side I'm trying to move things to. Sometimes it's really clear and obvious, and sometimes it's not so clear, not so obvious. So let that dy and dx guide you in where things need to go. So what I'm going to do then is get the y's together. I'm going to multiply the y on both sides, so I end up with y dy equals x dx. Now that I have both sides separate, so y is on the left and x is on the right, I now can find the antiderivative. Okay, I'm going to do this the formal way the first time through, and then I'll drop some of this formality later on. Let me show you what I mean. So the antiderivative of y dy, so the antiderivative of y with respect to y, is just 1/2 y squared plus some constant. And I'm going to call this constant c sub 1. Okay, now if I look at the right-hand side, if I find the antiderivative of x, that is 1/2 x squared plus a different constant, c sub 2. Now, what form do we need to write this equation? Like, where do we stop simplifying? A lot of times we try to get y by itself, sometimes we can't. So let's try to at least start getting closer to that. First thing I'm going to do is combine these constants together. So I'm going to subtract c1 from both sides. That's going to cancel out those c values. I have 1/2 y squared equals 1/2 x squared. And then if I take the constant from the x side and subtract the different constant from the y side, I'm still going to have a constant of some kind. It's just going to be different. So I'll call this c sub 3. Now normally I will not write all of these c's with subscripts, but for now I just want you to see that they are all different c values. They're not just going to all cancel each other out. Okay, the other thing I notice, I want to try to get rid of that fraction, that 1/2. So I'm going to multiply this entire equation by 2. If I multiply 2 times 1/2 y squared, I get y squared. 2 times 1/2 x squared, I get x squared. And 2 times c sub 3 is still a constant. So really what we're on now is our fourth different constant. So this is c sub 4 actually. Now trying to isolate y in this case is going to get ugly, because if we were to try to isolate y, I would have to take the square root of both sides, and then so many algebraic errors can happen. Really what should happen if you do isolate y is you would have to say plus or minus the square root of x squared plus this constant. But the tricky part is a lot of people forget the plus or minus, and then they try to take the square root of x squared and the square root of c to the 4th separately. And that's not possible because of the addition. So when y is squared, for the most part, we're just going to leave it that way. We're not going to get into this trickiness of trying to isolate y. So the last step then would just be this is a form of an equation that you may not be familiar with. This is a parabola. I don't think you've seen this in pre-calculus, but that's okay. And finally, for our last constant, c sub 4, I'm just going to drop that subscript of 4 and just say this is a constant. So this was the original equation that gave us the derivative of x over y. Let's try another one, and let's see if we can get it a little bit closer to y being isolated. Okay, let's look at this second example. We have y prime equals x times y plus 1, or 1 plus y. Y prime, I'm going to change y prime back into dy over dx because that's going to help you see which side the x's need to be on and which side the y's need to be on. So if I move the dx to the right-hand side, this is now telling me that the x's need to be on the right side and the y's need to be on the left side. Okay, in order for that to happen then, I need to divide by 1 plus y. So now I end up with dy over 1 plus y equals x times dx. Now that I have the variables separated, it's time to find the antiderivative. It might be helpful for you in order to figure out how to find the antiderivative of the left-hand side. It might be helpful to write this as 1 over 1 plus y dy equals x dx. Take a pause, go try both of these. Okay, welcome back. I'm going to find the antiderivative of the right-hand side first. And here's where my formality is going to disappear. I know that when I find the derivative of the left side, I'll have a constant. When I find the derivative of the right side, I'll also have a constant. I know that I will join those two constants together. So here I had a constant on the left, constant on the right. I combine them together into this constant. I'm going to skip this whole first step of putting a constant on both sides and moving the one over to the right side. I'm just going to say, when I find the antiderivative of x, I have 1/2 x squared plus some constant. And in my mind, I know it's the third constant because the first one was the left, the second was the right, the third one was when they were combined. So I know in my mind that this is really c sub 3, or the third constant that I've dealt with, but really I'm just going to say it's some constant called c. Now when I find the antiderivative of the left-hand side, I notice that this looks like it's probably in the form of u prime over u. U is 1 plus y, and since we're differentiating with respect to y because of that dy there, u prime is 1, or dy, however you want to call it. So u prime is 1. This is in the form of u prime over u. So the antiderivative is the natural log of 1 plus y. Plus a constant, of course, but I move the constant over to the other side. My goal is to try to isolate y, and in this case, I actually can. Because remember that natural log is the same thing as log base e of 1 plus y. So what I can do is rewrite this as an exponential equation to get rid of that logarithm. If I rewrite this as an exponential equation, I would say 1 plus y equals e to the 1/2 x squared plus c. So that entire right-hand side became the exponent of e. I'm going to do a little something fun on this right-hand side because I want you to see that this can simplify a little bit more. So I'm not going to mess around with the left side yet because I want you to see this right side. We've talked about this a few times now. Remember, this is an exponent, and these exponents are added. So I can separate these two into a multiplication problem. Because as long as the bases are the same, I can add the exponents. So if the exponents were added, I know the bases were multiplied. Well, e is a constant. C is a constant. So if I take a constant called e to a value that is also a constant, the result is also a constant. Now, I haven't been keeping track of how many different constants we're on right now, but this is just some value c, some constant value. I don't know what it is, but it's some value c. Last thing, I want to get y isolated, so I'm going to say y equals, I'm going to move the c out in front as a coefficient of e, 1/2 x squared minus 1. And we've isolated y. We have solved the differential equation. We found the original function that gave us this as the derivative. Okay, one last thing, we're going to put this into some kind of an application. So we're going to use this for somewhat of a purpose. So I'm going to ask you to write and solve a differential equation. The rate of change I should have had this written out already. I apologize. Feel free to fast forward. So the rate of change of P, let's just say it's a population, is proportional to the population. When T equals 0, so now we know what the two variables are that we're looking at. Instead of x and y, we have T and P. So at initial time, like when this was all started, the population was 5,000. And when T equals 1, P is 4,750. The question we're trying to find then is, what is the population when T equals 5? So let's work through this one. First of all, we need to write the differential equation, the rate of change of P. Now remember, our two variables are P and T. So we're looking at the rate at which the population changes over time. So the rate of change of P is dP over dt. Proportional means, and we've talked about this a few times, proportional means that it's equal to the population multiplied by some value. Some value k, not c. Even though k is a constant, it's a different constant. This k value is the constant of proportionality, not a y-intercept like plus c it gives us. So it's k times p. So here we go. We have our equation based off of this information. I've just written the differential equation. dP over dt, the rate of change of p, is equal to k times p. It's proportional. So now what we need to do is solve this. I'm going to, first of all, separate the variables. I'm going to move dt to the other side. So dp equals kp dt. Now I know that the t's are going to be on the right and the p's are going to be on the left. So that means I need to move this p over to the left-hand side. I'm going to keep k where it is because I'd rather not have more values in the fraction than I need. So I'm just going to divide both sides by p. So now I've got dP over P equals K times dt. Remember, K is just a constant. We're ready to integrate. If I find the antiderivative of the left-hand side, that's just u prime over u. U is P, u prime is dP. So this is the natural log of P, the natural log of u, plus some constant, but I'll just move it to the other side. The antiderivative of K is K times T plus a constant. All right, just like we did in the last example, I'm going to isolate P. So P is equal to e to the kt plus c. I'm going to separate this into kt times e to the c. So really this is the original function, where c is some original constant, k is the constant of proportionality. So let's use the information that was given. The first piece of information that was when t was 0, population was 5,000. So let's plug that information in. Population was 5,000 when time is 0. 0 times k is 0. E to the 0 power is just 1. So what that tells us is that c value. So we know where this population started. Okay? The equation now looks like this. We have a little bit more information. The second piece of information that was given to us was that when time was 1, or when t was 1, the population was 4,750. So we're going to use that information to find k. So we have 4,750 equals 5,000 e to the k times 1. My goal is to isolate k. So I'm going to divide by 5,000. I have 4,000. I'm going to go to the next line below. I have 4,750 over 5,000 equals e to the power of k. Now what I'm going to do is isolate that k by applying the natural log to both sides of this equation. So if I have the natural log of 4,700, I'm going to take off one of those zeros. I'm going to take off one of those to reduce this a little bit. And the natural log of e to the k. What that does then is it brings the k out in front of this natural log. And since we know the natural log of e is 1, we have just found the constant k. don't find this as a decimal. There's no need. You're going to be using a calculator anyway, and if you find this as a decimal right now, that will be rounding, and then you'll be rounding again. And since we're talking about exponential growth, the more exact we can make it, the better. So we finally have our equation with all of the values plugged in. K is, so it's t times the natural log of 475 over 500. We're finally ready to answer the question, because the question says, what is the population when t is 5? So if t is 5, what is the population? So now all we have to do is take the equation that we built and replace t with 5. 5 times the natural log of 475 over 500. And unfortunately, I don't have a calculator with me, but you can just put that into your calculator to find the population. Okay, that's a good introduction to these differential equations. We'll be spending a lot more time with them, but today is just an introduction.